This is what I lived on for a long time. So, if you're going to be there, you're going to need this. But other than that, it's part of the curriculum, and you got to do it. Got to do it.
So in real life, what do they use?
Well, define real life.
In your job.
In my job, okay. Let me kind of bullshit here a little bit, okay? Okay, in electrical circuits, you get what are called resistors, okay, capacitors, and what are called inductors, okay? And to make a mathematical model out of this thing, okay, the reason is that there's what's called a phase difference between the currents that go through these, okay? So in order to analyze this, when I say analyze, I mean mathematically analyze, write mathematical equations, write computer programs, simulate them, and do stuff. You need the concept of complex numbers. Okay, I mean, that's all I can tell you. I mean, I can throw out nasty equations at you, but it means nothing. But no, this is definitely used in electrical engineering. No questions about it. No questions about it. So no, it does have utility. Okay, so you guys get the theorem itself, and let's go. Where did it go? You guys get the theorem? So let's just go apply it then. Is Chirag doing W, or is he doing Chem-Eng? He's doing Chem-Eng. Okay, ask him if he knows if he's used complex numbers in his courses. If he tells you something, bring the story over, and we'll see. Okay, so recipes, okay? Let's go through the recipes. Step 1, convert to trig polar form, which you all know how to do, right? We just did that for a couple of problems. So, Sharik, what's R equal to? Root 2. Your plot's going to look like this, right? That's where Z is. What's the angle equal to? Sorry? Pi over 4. Is everybody with Ian on that? Everybody with Ian on that? Pi over 4. And so now your trig form of this guy becomes root 2 times cosine pi over 4 plus I sine pi over 4. Okay?
Would it ever be minus I sine?
No, it'll always be plus I sine pi over 4. Yeah. It would become minus if the angle in here becomes negative and you pull the sign out. Okay? Yeah, you can pull the sign out. But I'm saying that let's not even go there, because the convention is you're going to have positive angles. Okay? All right, so Demois tells you that if you want to raise this to the fifth power, like what it's asking you to do here, if you want to raise this to the fifth power, okay, then Demois tells you that what you do is you raise this to the fifth power. So remember, root 2 is to what power, first of all? 1/2. And so when you raise that to the fifth power, what do you get? So it'll be 2, 5 over 2. Okay, and we need to work on this a little bit more, okay? We'll work on it a little bit more. Then what do you do with the angles? Multiply by. You guys keeping track of time, right? Sabina, you taking care of the time, right? I don't know. I mean, come on. 30 minutes. Yeah, sorry, Sam. Okay, let's go back to our friend Demois. Right there. Okay, so that's Demois' theorem. In the example that we have, what is n equal to, Sam? 5. So 5 times theta. Theta was pi over 4. Yes? So it becomes 5 pi over 4. All right? Is that the question? Did I get you right? Oh, the 5 over 2. Oh, okay. Oh, you mean this guy here? This guy? Okay, what's the rule to do this math? from algebra 1? From there. Okay? So we need to fix this, okay? This is not good enough. What's 2 to the 5 over 2? So remember, 2 to the 5 over 2 is the same thing as 2 to the 2.5, right? So that's going to give me 2 times 2 times 2 to the half. What's 2 times 2? 4, and the other guy becomes square root of 2. You guys with me on that? So then this becomes 4 square root of 2 times cosine 5 pi over 4 plus I sine 5 pi over 4. Did I hear a no there, Laura? This guy here? Okay, 5 halves, 2 to the 5 halves is the same thing as 2 to the 2.5. Right? Which is the same thing as 2 to the 2 times 2 to the half. Using laws of exponents from way back when. So what's 2 to the 2? 4, right there. What's 2 to the half? Square root of 2, right there. Okay? Alright, now I want to kind of reiterate the old-fashioned way so that you feel the pain, and I'm going to do it in red. Okay? The old-fashioned way to do this guy would have been to do what? How many times over? How many do I have so far? So you're gonna foil this guy first, right? Okay, let's do it. So I want to feel the pain. That's why the red there. 1 plus 2r, exactly, right? And then you're going to go 1 plus 2. Anyway, you guys feel the pain. I do already, okay? Did you see how Demoir made life so easy for you? Do you appreciate him? Would you say French are good people?
No.
Yeah, what a racist, man. Okay, I think I'm done. Let me see if there's another example for you guys to work on. Yeah, really. Okay, you guys do, I guess. Yeah, you do.
What?
You do.
Do what?
That F problem, hello? Alright, everybody got that? And then you hit enter and you should get 4096. Now notice what you've got there. You got plus 8.192 e to the minus 10 I. What's e to the minus 10 look like to you? Itsy bitsy number? Good enough for 0? Okay? That's because of the imprecise nature of this calculator. Okay, it's called digital, and you get kind of errors in doing that. So everybody know how to use a graphing calculator to do complex numbers then? Rush. You're looking at me like I'm an alien. I am an alien, but yeah, like the other kind of alien. Is everybody okay? Does anybody need help on the 84? Okay, I'm done then.